fall asleep, right? So from waking state, they want to go to sleep. You really plan after that? Okay. So when they go to stage 1 of the sleep, okay, there's a change in the EEG from here to here. So in wakefulness, we have beta waves in the EEG. But when the sleep starts, we have a specific type of wave called sleep spindle. So sleep spindles are like this. They are alpha waves that are large, and they appear for only 1 or 2 seconds, and after that they disappear. So after a while, again they reappear. So we have intermittent appearance of these sleep spindles. So we call this stage 1. So the person remains here for some minutes and then goes to stage 2. So sleep becomes deeper, right? And the EEG is converted into theta waves. So we see theta waves in stage 2, and after that the person goes to deeper sleep, stage 3. So they have theta waves and sometimes delta waves, right? Theta and delta waves. Then the person goes to stage 4, the deepest one, and the EEG becomes delta waves. So in stage 1 we have the sleep spindles, in stage 2 we have theta waves, in stage 3 we have theta waves again, but sometimes there are delta waves, but in stage 4 we have delta waves, right? So deep sleep is called is the stage 4 of this sleep. So from here, stage 1 to stage 4 usually takes 30 minutes. And the person remains in stage 4 for another 30 minutes. And then the person comes back to stage 3. So delta waves becomes again theta waves, right? Then he or she enters stage 2. And after that, they go into another phase of sleep called REM sleep, or REM, right? Rapid eye movement sleep. So we have 2 phases of sleep: rapid eye movement sleep or non-REM, or slow wave sleep. So because from here to here, the waves are getting slower and slower, we call them slow wave sleep. It's studied with, right? So slow wave sleep. Slow wave sleep. So stage 1, 2, 3, 4 are called slow wave sleep, and this one is called REM sleep, or rapid eye movement sleep. And this is a cycle of sleep. So from here, from the start of the sleep to the end of the first REM is called one cycle of sleep. It takes about 90 minutes. So 90 minutes for a cycle of sleep. And you can see that we have 4 to 5 of these cycles. So during the night, we have 5 cycles of sleep that takes about 8 hours, right? One thing that I should mention here is that in cycle 1 and cycle 2, we have deep sleep, stage 4 sleep. But in other cycles, we may not have deep sleep. So the person enters stage 2, stage 3, and then from stage 3, he or she goes back to stage 2, then they go to REM sleep. So stage 4 sleep is missing from the cycle 3 to cycle 5, right? So as we go through the sleep, the depth of the sleep becomes smaller, right? So sleep becomes lighter. But the duration of REM increases. You can see that in the first cycle, the person has a small or short REM, but REM sleep increases in duration and becomes longer and longer as the person goes toward the end of this sleep, right? So this is the pattern of changes in the stages of sleep during the night. So, we have two phases of sleep, slow wave sleep and REM sleep. So, physiological parameters that change during the REM sleep include this. You can see that brain waves in the slow wave sleep become strong and low frequency. So we start from beta wave, then alpha, sleep, then theta and delta, right? So frequency decreases, amplitude increases. So we have strong waves, frequency, voltage and amplitude. And we have low frequency waves. Slow wave sleep is very restful. That's why in the first and the second state, in the first and second cycle of sleep, we have a stage 4, which is deep sleep, so it's very restful. And there are decreases in muscle tone, body movement, heart rate, respiratory rate, blood pressure, basal metabolic rate, and temperature. So all of these decrease during the slow wave sleep. So tone of the muscle is lost, decreases, body movement decreases, heart rate decreases, respiratory rate. You can see here, right? So we have a stage 1, 2, 3, 4, and then 3, 2, REM. Right? So what happens to heart rate? So from a stage 1 to stage 4, decrease in heart rate. What about respiration? Again,
decrease.
So when we go from a stage 4 to REM,
increase.
there is an increase in the heart rate and respiratory rate, right? But in the REM, you can see that heart rate and respiratory rate is very variable. Sometimes it's very high, some other times it's very low, but the mean is similar to wakefulness, right? So we have increase of heart rate and respiratory rate during the REM sleep in comparison with the stage 4 of the sleep. So here you can see EMG, electromyograph. I told you it's used for measuring tone of the muscle or contraction of the muscle, right? So you can see that when we go from stage 1 to 4, there is decrease in tone of the muscle. So all over the stage 4, tone of the muscle decreases. EOG, electroacuography. So you can see that in stage 4 mainly, and also in other stages of a slow wave sleep, we don't have electroacuographic waves, right? It means eyes are not moving. But in REM sleep, we have eye movement, so that's why we call this rapid eye movement, right? So, REM sleep occupies 25% of the total sleep time. In young adults. In children, it's more. In newborn, it's more than 50%, right? But in adults, it's only 25%. It's an active form of sleep because eyes are moving very fast, and it's associated with dreaming. So, actually, dreaming also happens in the slow wave sleep, but dreaming during the REM sleep is different in quality. So we say that REM dreams are vivid, means clear. So we can remember every detail of the REM dream, right? So it's vivid, it's long, it's visual usually. So you know that dreaming has several components: visual component, hearing component, smell, touch. All of them happens in dreams, right? But the main component in REM dream is visual component. So we see anything during the dream, right? And it's emotional usually. But non-REM dreams are dull, right? And vague actually. So if you cannot remember the details of the of the dream, right? And they are shorter, less visual, and less emotional, and more conceptual, right? Conceptual and logical, non-REM dreams. But REM dreams are emotional and bizarre, means strange, right? So, there are differences between REM and non-REM sleep. And during the REM sleep, muscle tone is exceedingly depressed, so we have atonia or atonia, right? Irregular muscle movements may happen, for example, in smaller muscles like twitch-like activity of the fingers, eye movements, so eye muscles are active, right? The threshold of arousal for bisensory stimulation is elevated, so it's more difficult to arouse the person by calling or by touching, okay, by sensory stimulation. I mean, heart rate, respiratory rate become irregular. The brain is very active, so metabolism of the brain is high. 20% increase in the metabolism of the brain happens during the REM. And during the REM, we have beta waves also. Okay? So the brain is very active because the person is usually dreaming, right? Temperature regulation is at the low point, temperature goes down, right? So these are some changes in parameters, in physiological parameters that happen in the REM. So why and how these changes happen during the sleep? I mean, what are the mechanisms for being awake and mechanism for sleeping? So in the past, scientists believed that in the day we work, we think, so the brain is active. It means action potential is made continuously. So after a while, the brain gets tired, and this tiredness causes sleep. The neurons cannot continue to fire action potential, they do sleep. But now we know that in order to fall asleep, we need activity in some areas of the brain. So sleep is an active form of state, conscious state. So it should actively be made, actively generated, right? So let's see the mechanism for sleep and wakefulness. So everything was started by some works done in 1930s by Brenner. So you can see here that we have a cat brain. So if we cut cat brain from here in the midbrain and record EEG from the rest of the brain in the forebrain, we'll see a high voltage, low frequency wave in the EEG, which is representative of what I told you in stage 4 we have delta wave. Delta waves are high amplitude and low frequency. After cutting midbrain, EEG in the rest of the brain becomes delta wave. It shows sleep. It is representative of sleep, right? So this part of the brain is sleep. But if you cut the brain from here, above the spinal cord, below the middle, right? Then EEG shows low amplitude, high frequency wave, which is indicating of wakefulness, right? So, based on this, they concluded that there is a region in the brainstem that sends the axons to the cortex and keeps the cortex awake. If you cut the midbrain, then you will cut these fibers. Cutting these fibers means they cannot keep the brain active. So the brain falls asleep, right? So, ascending projections from the rostral pons and caudal midbrain are necessary for maintaining arousal, right? So, another experiment. If you stimulate reticular formation in a sleep cat, The cat's awake. Is wake, right? So it means the stimulation of the reticular formation promotes wakefulness. But stimulation of thalamus promotes sleep. So these are other experiments. So everything is located in the brainstem, especially in the pons and in the midbrain. So in the pons and midbrain, we have an excitatory area that sends the axons to the cortex, activates the cortex. So if you record the EEG from this cortex, you will see high frequency, low amplitude waves, beta waves. But there is another region here in the lower part of the pons, which is inhibitory area. So this inhibitory area inhibits the excitatory, so fibers cannot activate the cortex. So it promotes sleep. Right? So this figure is not so precise. This excitatory area is located above the mid part of the pons. Okay? So it should be here. So in the midbrain and the upper part of the pons. And this one is located in the lower part of the pons. Right? So what do we have in these areas? We have several collection of neurons. Some of them release norepinephrine, like locus coeruleus. Other neurons release acetylcholine. We call them gigantocellular parts. Substantial nigra, which releases dopamine. Serotonin neurons located in the raphe magnets or raphe nuclei, right? So these are part of the reticular formation located in the upper pons and midbrain. So they provide, they activate the brain and promote wakefulness. But this one is the newest one, okay, based on the most modern studies related to sleep and wakefulness. So you can see that in the pons we have the locus coeruleus, which releases norepinephrine. We have hierarchical nucleus, which releases glutamate. We have pedunculopontine nucleus, which releases both glutamate and acetylcholine. We have raphe nucleus, which releases serotonin. Right? What else? Tuberomammillary nucleus, which releases histamine. Supramommillary nucleus, which releases both GABA and glutamate. Basal forebrain, which releases GABA, acetylcholine, and glutamate. Right? So all of these send their axons toward hypothalamus, and then from hypothalamus toward the cortex. They go from inside the hypothalamus, and then they go up to the cortex, right? So other nuclei send the neurons to thalamus, and then from thalamus, other neurons go to the cortex. So we have two pathways. One pathway through the thalamus, another pathway through the hypothalamus. So they go to the cortex, they release these neurotransmitters, all of these. And these neurotransmitters activate the cortex and promote wakefulness. So remember from our previous part, I told you that if thalamocortical inputs are activated, then we'll see some waves in the EEG. Right? If corticocortical inputs are activated, so activity in the cortex increases. So we see EEG waves. And I told you that synchronized activity from thalamus causes low frequency waves. Irregular activity from thalamus promotes high frequency waves. Right? So when thalamus is active, thalamocortical inputs are also active. So they promote high frequency waves. So the brain will become actually more active and consciousness increases. So all of these are important for wakefulness. So based on this, you can predict the effect of some drugs. So if you give an antihistamine drug, antihistaminergic drug to a patient, it will lower consciousness. It will cause sleepiness. Why? Because histamine is one of the neurotransmitters that increases wakefulness, involved in wakefulness. Right? So when you block the receptors, the person will become sleepy. Right? Or, for example, if you give some drugs that increase norepinephrine in the brain, then the level of consciousness increases. Right? So, and cholinergic drugs also. Cholinergic drugs increase the level of wakefulness and consciousness. So, and what happens if there is any damage in this region? So, if there is any damage in this part, in midbrain, in diencephalon, then these neurons are injured, right? So they cannot send the neurotransmitter to the cortex. EEG becomes slower and stronger. So the person actually loses his consciousness. So the result is coma. So coma can happen after damage to the cortex because the cortex is everything. So we need the activity in the cortex. If the cortex itself is not active, it means the person is in coma. Or maybe it happens after damage to the subcortical areas that provide activity in the cortex. Right? So, especially in the midbrain and also in other parts and regions that include thalamus and hypothalamus. So try to memorize these neurons because they are very important for wakefulness, right? So, this figure shows the level of activity in cholinergic neurons and norepinephrinergic neurons. So let's see this one. So here we have the state of wakefulness, slow wave sleep, REM sleep, another wakefulness, right? So here you have the firing rate of neurons. Which neuron? Locus coeruleus, which releases what? No, norepinephrine. So norepinephrine is a neurotransmitter that promotes consciousness, right? So this is from rat. Okay, when the rat is conscious and awake, norepinephrine neurons in the MC generate 4 action potential per second. So high action potential, high rate action potential. When the rat falls asleep, the level of activity decreases. So norepinephrinergic neurons becomes slower, right? So they generate lower rate of action potential. During the REM sleep, these neurons stop firing. They are silent. Then the rat is wakened again, right? So in the next wakefulness, you can see that firing rate increases again. So in wakefulness, locus coeruleus neurons are very active. Slow wave sleep, they decrease firing. In REM sleep, they stop firing. Right? So let's see another one. Acetylcholine neurons, where in the basal forebrain. Right? So in the basal forebrain, acetylcholine neurons are very active during wakefulness. In non-REM sleep, slow wave sleep, they decrease firing. In REM sleep, they are again very active. So in wakefulness and REM, they are active. In non-REM, they are actually less active, right? So let's see from the other side. When both norepinephrinergic neurons and acetylcholine neurons are active, you are awake. When both of them decrease their firing, you fall asleep. Which stages? Slow wave sleep. Right? When norepinephrine neurons stop firing, but acetylcholine neurons increase firing, you are in REM sleep. Right? So we only mentioned here 2 types of neurons. Norepinephrine and acetylcholine. So other amines like serotonin, histamine, dopamine follow this pattern. So during wakefulness, norepinephrine, dopamine, serotonin, histamine, all are highly active. In slow wave sleep, they decrease it. In REM sleep, they stop fire. Right? But acetylcholine is different. In REM, it increases. So I told you before that in wakefulness, the brain activity is beta, then frequency decreases in the slow wave sleep, and in REM sleep again it's beta. Because in the REM, the brain is very active. And this activity is caused by acetylcholine. At least one of them is acetylcholine. Right? So, what about sleep? So earlier studies have shown that stimulation of raphe nuclei in lower part of the pons and in medulla promotes the sleep, causes the sleep. NTS, nucleus tractus solitarius, activation causes sleep. In the anterior part of hypothalamus, mainly suprachiasmatic nucleus, if you stimulate neuron, it causes sleep. Yesterday I told you that suprachiasmatic nucleus is mainly involved in circadian rhythm. Right? So, midline nuclei of thalamus. If you stimulate them, it will cause sleep. What happens if you remove these areas? For example, if you remove these areas, what happens? The animal cannot fall asleep. Never. The animal even die of tiredness, but it cannot sleep. So, it shows in order to fall asleep, we need activity in some areas of the brain, not overall inactivity. Okay? Some areas should be active. Which areas? Raphe nuclei, thalamus, part of the hypothalamus, right? And other areas. Another important thing about the sleep is that when you keep a rat awake for several days, some neurotransmitters, some chemicals accumulate in the brain. If you draw these neurotransmitters and inject them to another animal, the next animal or the second animal fall asleep. So we call them somnogens. One of them is muramid peptide. The next one is sleep, delta sleep inducing peptide. So they accumulate in the CSF and they cause sleepiness. And more important than these is adenosine. Adenosine is another chemical which increases in the brain after sleep deprivation. Right? So it causes sleepiness in the person or in the brain. So now, the newest studies about the sleep shows two regions that are very important for sleep. One is here in the hypothalamus. Another one is here in the brain. This one is called VLPO, ventrolateral preoptic nucleus. Ventrolateral preoptic. Right? So neurons from here go down to the diencephalon brainstem and inhibits all of other neurons that were active during wakefulness. I told you that we have acetylcholine neurons, dopamine neurons, serotonin, norepinephrine, histamine, and also other neurons. All of them make the brain active. They are important for consciousness, right? Damage to these neurons causes coma. But there is one nucleus in the hypothalamus that inhibits all of these. Which nucleus? Ventrolateral preoptic nucleus. It releases GABA and GABA. Both of them are inhibitory neurotransmitters. So all of the activating system neurons are inhibited. So the result is sleep. Another region which is important for sleep is this one. Parafacial zone. Parafacial zone. So it has GABA neurons that inhibit only this one, parabrachial nucleus, which releases glutamate, right? So PFZ neuron inhibits parabrachial nucleus, and this also causes sleep. So we have several neurons, several nuclei related to wakefulness, and 2 nuclei for sleep, at least 2 of them, right? So PFZ, parafacial zone, and ventrolateral preoptic nucleus. So I told you that acetylcholine neurons are important for REM sleep. So let's see connections of the neurons. So in the pons, we have an area called subceruleus region. Subceruleus. It has mainly glutamate neurons. So you can see that, so these blue lines, right? Glutamate neurons go upward, they reach basal forebrain. Some of them go downward in the spinal cord. Those that go upward activate acetylcholinergic neurons in the basal forebrain, and these neurons go to the cortex, right? So when these neurons are active, basal forebrain is active, cortex becomes active. The result is REM sleep. Why some neurons go downward? So they go downward and cause atonia, loss of tone of the muscles. During the REM, we have atonia, tone of the muscle is lost. This atonia is made by these glutamatergic neurons. But subceruleus neurons are under control of other regions. So you can see that, for example, pedunculopontine nucleus, lateral dorsal segmental nucleus, release acetylcholine. Acetylcholine activates this region. The result is REM sleep. Right? Another one is this one, orexin neurons. But before that, let's focus on this. We have ventrolateral PAG, periaqueductal gray region. So neurons here are GABAergic. GABA neurons from here come in the subceruleus region, inhibit glutamate. So they stop REM. They prevent REM sleep, right? But the same population of neuron is activated by orexin. Orexin from hypothalamus, from lateral hypothalamus. So orexin from lateral hypothalamus activates PAG neurons, ventrolateral PAG. Ventrolateral PAG inhibits subceruleus. So they inhibit REM sleep, right? So acetylcholine activates REM, orexin inhibits, right? So we'll see this in the final slide. Okay, we need this orexin. Okay, now let's focus on this one. How this causes atonia, because it's glutamate. Glutamate is excitatory, so it should activate muscles. But why muscle loses its tone, right? So let's see here that from subceruleus neurons, we have glutamatergic neurons that go down through the spinal cord. They reach the anterior cord, activate some interneurons. Interneurons inhibit alpha motor neuron. Alpha motor neuron is inhibited, so muscle is relaxed. Another pathway. Subceruleus neurons go to ventral gigantocellular neurons in the middle. They are GABAergic. They go down through the spinal cord and directly inhibit alpha motor neurons. So alpha motor neurons are inhibited. Right? When they are inhibited, muscle is not activated. So muscle is relaxed. So that's why the person is relaxed during the REM sleep. Right? So, we have seen several neural mechanisms about this sleep. You should remember that in the upper parts, in the midbrain and hypothalamus, we have different type of neurons that promote wakefulness. What are they? You name it. What are those neurons involved in wakefulness? Acetylcholine from peduncular pointing nucleus, lateral dorsal tegmental nucleus. What else? Norepinephrine from locus coeruleus. Very good. Histamine from tuberomammillary nucleus in the hypothalamus. What else?
Epinephrine?
Not epinephrine, no. Norepinephrine from locus coeruleus. Dopamine from substantia nigra and also ventral tegmental nucleus. Okay, what else? We have one more.
Glutamate.
Glutamate from parabrachial nucleus. But we have one more. Serotonin. Serotonin from where?
Rubonic.
Raphe magnus. Raphe nuclei. Dorsal raphe nuclei. So remember, raphe nuclei are spread all over the brain. So raphe nuclei located in the upper pons and midbrain promote wakefulness. But raphe nuclei located lower than these promote sleep. Okay? So they use different type of receptors. So their result, the result of their activity is different. So if serotonin neurons for the upper pons and midbrain are active, the result is wakefulness. If raphe nuclei lower than these are active in medulla and up and lower parts, right? They promote sleep. And I told you that if you remove the raphe nuclei, the rat cannot sleep, right? So, mechanism for atonia, and you also know the mechanism for REM sleep. Subceruleus region is the main region for REM sleep. It has glutamate neurons. Glutamate neurons go to basal forebrain to activate acetylcholine. And acetylcholine activates the brain, right? Acetylcholine neurons from lateral dorsal tegmental nucleus, peduncular pointing nucleus activates the subceruleus. So they promote REM. But PAG neurons inhibit subceruleus. PAG neurons inhibit subceruleus, so they prevent REM. The same region, this one, is under the control of orexin. So orexin activate this, so this one inhibit this. So they can prevent REM, right? So there is a disease called narcolepsy. It's an abnormal activation of sleep mechanism. Abnormal activation of the sleep mechanism. So a person with narcolepsy has several problems. The first one is called excessive daytime sleepiness. Excessive daytime sleepiness. So the person experiences sleep attacks. Unwanted sleep attacks. Right? That lasts for about 20 minutes. The person cannot resist this attack. Okay, when it comes, there is no way for the person. The person falls asleep. Right? So, passive and boring behavior actually facilitates this sleep attacks. So another one is cataplexy, a sudden bilateral loss of muscle tone. So muscle tone is suddenly lost, the person falls down. Right? So we call this cataplexy. But the person falls down, but he or she is awake and conscious. Right? So he knows what is happening. Right? So it lasts for only some seconds. Some emotions usually promote cataplexy. For example, when they laugh, they fall down. Okay? So it results from abnormal activation of motor inhibition. Another symptom, hypnagogic, hypnopompic, dreamlike hallucinations. So dreamlike hallucinations happen at the beginning of the sleep or exactly at the end of the sleep. The person knows that the images are not real, and he or she is not dreaming. The person is aware that these are hallucinations, are not real. Okay? So, another problem is sleep paralysis. So, at the start or at the end of the sleep, the person is still awake, the person is conscious, but he or she cannot move any part of the body because all body parts are relaxed and paralyzed. And it's very stressful for the patient, right? So it lasts longer for several minutes, and the person is unable to make even the smallest of movements. And the last one is disturbed nocturnal sleep. Short latency of the sleep and an interrupted pattern of sleep. I told you that we start our sleep with the stage 1, then go to stage 2, 3, 4, then back to stage 3 and 2, and then REM. Then we have several cycles of this. These people usually start with REM. Right? So they are awake. Then at the start of the sleep, they have hallucinations sometimes. Right? Then they start dreaming, REM sleep, and then they go to slow wave sleep. So the pattern of the sleep is disturbed. So the reason for this problem is a lack of orexin units. Right? So let's see. This is part of the hypothalamus. This one is from the brain of a normal person after the death. So after the death, the brain was removed, it was fixed, then it was cut, right? The cut that has hypothalamus was stained with a specific dye, specific stain, specifically actually stains orexin neurons. So these dots are orexin neurons. So this is fornix. I told you before that this side is lateral hypothalamus, this side is
Medial.
medial hypothalamus. So you can see that orexin neurons are mainly in the lateral. Some of them are in pericortical areas. We call this pericortical areas. So in the brain of a normal person, we have a few thousands of orexin neurons in the lateral hypothalamus. But in the brain of a narcoleptic person, we don't have any orexin neurons. Right? When there is no orexin, what happens? Yeah. I told you that orexin activates PAG neurons. PAG inhibits some steroids. So this way, it prevents REM. Right? When there is no orexin, this one cannot be activated enough. It cannot inhibit substeroids. So REM happens in an uncontrolled manner, even during the wakefulness. Right? So orexin is also part of the activating system. Let's see here. So neurons that are important for consciousness include waking neurons, leukocytes neurons, and so on. Here we have also orexin neurons. So orexin part of the brain activating system. Right? When there is loss of orexin neurons, it means the patient will become sleepy. So during the day, in the day, they have sleepiness, but sometimes they show signs of REM sleep. Right? So hallucinations is similar to dreaming. Right? Cataplexy, they fall. It's similar to atonia. Atonia that happens in the REM. Right? So they show signs of REM, not during the sleep, but during the REM. And at the start and at the end of the sleep, they show paralysis. All of the muscles are relaxed. Again, we have atonia. Right? Okay, that's all about sleep and wakefulness. In the next session,